Okay, well, welcome to ME3150's tension experiment. And in this experiment, what we're going to be doing is doing what is probably the most important material test as far as characterizing materials and extracting material properties, and that is a tension test. And so for this test, what we're going to be doing is we're going to be starting out with a dog bone specimen. We have two of these. One of them is aluminum, the other one is steel. And you're going to be taking a look at the properties that you extract from the tension test to try to come up with an educated guess as to what kind of steel we have over here and what kind of aluminum we have over here. The tension test can be done on a variety of kinds of specimens. These particular specimens are flat, as you can see, so they're we'll take the measurements in just a moment, but there's grip areas on the top and the bottom which are going to be placed in wedge grips and grabbed. And then you have a gauge section where the cross section of the specimen has been narrowed in order for most of the deformation to be concentrated over here and not in the grip sections. And you have fillets in the transition between the grip section and the gauge section so that you don't have a sudden change in stress and a stress concentration. So what we're going to do is we're going to measure the dimensions of the specimen. We're going to use a pair of digital calipers over here, and we're going to measure the width of the specimen, the thickness of the specimen, and the separation between the two fillets, which is the total gauge length of the specimen. And those we're going to enter into the machine. The machine is going to be calculating strain in two different ways. The kind of crude calculation of strain, which it can always do, is it can just measure the displacement of the ends of the specimen as it's pulling one end apart. So when it calculates the strain in that way, what it's going to take is it's going to take as the deforming length, the distance between this fillet and that fillet. So that's why we put that in there. And that measurement of strain is going to be used from the beginning of the deformation all the way to the end of the deformation. That measurement of strain is very versatile in the sense that you can do it all the way until the specimen breaks and it's not a problem, but it's not super accurate because when I put this specimen into the machine over here, the displacement of the bottom part of the machine is clamped, so this bottom grip is stationary. The top grip travels with the crosshead. So when I turn the machine on, the crosshead is going to travel upwards, and the displacement that is being measured is how far up did the crosshead travel. But how far up the crosshead travels is not exactly the same as how far up the top of the specimen travels, because there's also some compliance in the load train. As I go up and the load builds up, this load train stretches a little bit too. So that's not a super duper accurate measurement of strain. As long as you're going to large strains, like the strain to failure, then this measurement of strain is fine, because the errors in it are fairly small. But if you need accurate measures of strain, like for example for determining the yield strength of the specimen, you need like 0.2% offset. In order to measure the elastic modulus of the specimen, you need very accurate measures of strain, and if you have that compliance of the load train built in, you'll get large errors. So when we want to have super duper accurate measurements of strain, what we're going to do instead is we're going to use a delicate but very accurate machine called an extensometer. And what this extensometer has is it's got two jaws that travel only a very short distance apart, but over that short separation distance, it's super duper accurate. So I'm going to mount this extensometer onto the center of my specimen after I have it in the machine. We're going to make we're going to measure the displacement of the specimen over a 1-inch gauge length for just 1% of the deformation, and that will allow you to do your calculations of the modulus and the yield strength. And then we'll stop the machine, remove the extensometer, and then continue on using the other cruder measure of strain all the way to failure. And the reason for that is that if I leave the extensometer on when the specimen fractures, that will break the extensometer, which is not a good idea. This is like a $10,000 piece of equipment over here. So what I'm going to do is, we're going to give you the measurements for the cross-section of the specimen, width and thickness, and also the distance between the fillets over here, the gauge length for both the steel and the aluminum specimens. For the post-processing, after your specimen breaks, you're going to want to calculate the percent elongation and percent reduction in area of the specimen. And for that, you need measurements of how much the specimen elongated relative to its original length. And then you need a measurement of the fractured cross-section of the specimen to compare to the initial cross-section of the specimen. So the fractured cross-section of the specimen, we'll have to measure the broken specimen's width and thickness, and that we will do after the specimen is fractured. In order to do a percent elongation, you could theoretically just reassemble the specimen after it's broken and then say, well, how much did these two fillets, which started out at the initial gauge length of the specimen, how far apart are they now? So you could use that as your final length for a percent elongation calculation. You could also, for a percent elongation calculation, take the final plastic engineering strain and multiply it by 100%. That's an alternative measure of the percent elongation. A third alternative for measuring percent elongation, and this is something that people typically do during tensile tests, is to take a pair of punches which have a separation of exactly 2 inches, like this, and then you take that and you put it on your specimen in the center of your specimen, and then you whack the center of the specimen with a hammer in order to put 2 little indentations on the specimen. Now, what you want to do is you want to make sure that the indentations are deep enough so that you can definitely see them, but you don't want to wang down on the specimen, because if you put too deep of an indentation on there, then you're creating a large enough stress concentration that that'll change the results of your test. Okay, so after we have punched the specimens, we're going to enter the dimensions of our specimen, the thickness, width, and length into the machine over here. Now I'm going to calibrate the 2 sensors on the machine that always have to get calibrated, which is, the first one is the load cell, this object up here, which measures the load that's being applied to the specimen. The second one is the extensometer that I showed you earlier. So first I'm going to calibrate the extensometer, and in order to do that, what I do is I press these 2 buttons together. What pressing those 2 buttons together does is fix the separation between the knife edges on the extensometer at exactly 1 inch. So then when I do the calibration, it knows that this is exactly 1 inch, that's the starting point. So I'm going to click over here the little button that says extensometer on it, and then I'm going to push calibrate, and it says put the extensometer on its gauge length, which it right now is. I say OK, and then it does an electronic calibration. In just a few seconds, the strain reading will come up as 0. And that's done. So you can see over there the strain is pretty much reading 0. So I'll hang this up for right now and then calibrate the load cell. In order to calibrate the load cell, I click on the button over here for the load cell, push calibrate. It says make sure that you don't have any loads on there. So right now the only load is the weight of the grips, which we want to tear out, T-A-R-E. So I'm just going to push calibrate over there, and then it will factor in the weight of the grips and set the load at 0, accounting for the grips. So there we have it. So this can read up to 10,000 pounds, and right now it's reading 0.05 pounds, so that's a very, very small load. So that's done, and now what I'm going to do is I'm going to mount our first specimen. So what I'm going to do is you can jog the crosshead up and down with these 2 buttons over here. So I'm going to set the separation of the jaws so that it's gripping nearly all of the top and bottom grip sections, but doesn't intrude into the gauge section. And then these are self-loading wedge grips, which means that when you tighten them, you can tighten them just kind of a little bit, and then as the load increases, the wedge grips get driven together, and the grip force increases as the axial force increases. So that's a nice feature about them. When I put my specimen in, I'm going to take care to do a few things. First of all, I'm going to make sure that my specimen is centered in the grips, right? Because if the grip is over here and you're at the edge over here, then in addition to the axial force, you're also going to have a bending moment. I'm also going to make sure that my specimen is aligned vertically, because if my grips are over here and your specimen is like that, then in addition to tension, you have shear, both of which are sources of systematic error. So I'm going to put my specimen in here, separate the grips so that they're not grabbing anything but grip area, and then tighten the top one, and then tighten the bottom one. And now I'm going to mount my extensometer on there. Remember, we're going to use the extensometer to measure strain in the very small strain value area so that we have accurate readings for that. And the way you mount and dismount the extensometer is you push these two buttons together to make sure that your extensometer is exactly 1 inch wide when you put it on. Then you pull the springs apart. These springs attach the extensometer to your specimen. So I'm going to pull the springs apart, slide this on my specimen, let go of the springs, then let go of the button, and the extensometer is going to be hanging on the specimen exactly 1 inch apart. Yes, in addition to the fact that this pushing of the button sets the length of the two wedge grips exactly 1 inch apart, there's another important reason for pushing those buttons when you're mounting and dismounting the extensometer, which is that this is a very delicate instrument. And if I were to just take this and pull the springs apart and kind of jam it on there, it would be very easy to destroy it. When you push these two buttons, that fixes the location of the arms of the extensometer, and it protects it during mounting and dismounting. So I'm going to mount the extensometer now on the center of my specimen. I'm going to let go of the springs. I'm going to support the bottom of the extensometer, gently let go of the button, and then let go of the extensometer. And what I should have is a strain reading of nearly 0. What you can see is the strain is reading 0.0038, so that's 0.4%, which is good. So I want to zero that out, but if this reading were like 1%, 2%, something like that, that means that I did a bad job of mounting the extensometer, and I need to take it off and remount it. But when the strain is this small, I can just zero it out by pushing the extensometer button over here and then pushing balance. So now my extensometer is starting reading from 0. You'll notice that the load, which we had calibrated to start from 0, is now reading 154 pounds. That is a real load. These wedge grips are not perfect. As you clamp them shut, they kind of go upward as well, so they actually introduce some tension into the specimen. But these specimens are going to fail at thousands of pounds, so a starting load of 150 is not that bad. So now this thing is all mounted. What I'm going to do is I'm going to lower the shield to prevent any shrapnel or any flying pieces of objects from hitting me. And then what I'm going to do is I'm going to push next, and this brings up the graph. In fact, why don't I magnify the graph for you so that you can see exactly what's going on. On this axis you'll see tensile stress in PSI. On that axis you'll see strain in inches per inch. And we are going to zero the extension so that we can come back to this separation. And now I'm going to start the test. And as I start the test, you'll see the tensile stress rise up during the elastic portion. You'll see the yield. The load will keep going up until you get to ultimate tensile strength, and then it'll drop down, and then eventually we'll get fracture. So let's do that. So the thing is self-scaling, so that as the stress goes up, it goes up. And this was the elastic portion, you can see. Now it's yielded. Now it's going up. The load is at 6,000 pounds, and now it's stopped because I reached 1% strain. I'm going to remove the extensometer and let the experiment go on until the end. Okay. And so now I'm going to continue over here. That little dip is an artifact of the fact that we stopped it. It's not real. So really the load would have continued from there on to over there. So we reached 6,050 pounds, and now the load is dropping. So we're already past the ultimate tensile strength, which you're going to calculate from the Excel data of the load versus displacement. And now you can see the load is starting to drop, and very soon there will be a loud bang and the specimen will fracture. Okay, so the specimen is fractured, so I'm going to, at this point, raise the shield, unload the specimen, take it out. And you can see the fracture over here. You can see that there's been necking, and the area where the fracture occurred is significantly thinner than the rest of the specimen. And we're going to measure the percent elongation. We're also going to measure the thickness and the width of the fractured section of it. And it's really kind of cool to take a look inside there too. So I don't know if you remember from your ME 3150, the fact that there's shear lips over there, and then there's void nucleation and growth on the inside of the fracture. It's pretty cool to look at a ductile fracture surface. Okay, so that's the steel specimen. And so now the way that we would do this now is I'm going to return the crosshead back to the original location, and we are going to save this data. So I'm just going to go save as, and then save the data to a location that is convenient. We'll make a new file for it, which we're going to call tensile data. And then save that. Okay, and now I'm going to finish the specimen, where it's going to save all of the raw data there. It says finish the specimen, and then it says, do you want to do another specimen with the same parameters? The answer is yes, because I still have to do my aluminum specimen. So now I'm going to take my aluminum specimen, mount it up, and now you've already seen this process done once, so I'll go through there fairly quickly. And then you run the test, and we'll see if the aluminum behaves any differently. So there's the elastic portion of the test. And it yielded at 3,000 pounds instead of closer to 6,000 pounds. So that's the low strain portion of it. We have enough information to calculate yield and elastic modulus. So I'm going to remove the extensometer and then roll for the rest of the test. And you can see the load is still going up, actually. 3660, 3670, 3680. And it topped out, no, still going up. There we go. It topped out at 3,700 pounds. And now it's starting to go back down again. So 3,700 pounds was the load at ultimate. And I'm going to remove it. And there you have it. And you can see actually the fracture is quite different between the steel and the aluminum. The aluminum, if you notice, the percent reduction in the area is fairly small. It's just a clean shear fracture. This one necked a lot. The steel necked a lot. The aluminum didn't neck very much. So it's interesting to take a note of that, and you can take a look once you've calculated the elastic modulus, yield strength, ultimate tensile strength, percent elongation, percent reduction in area. You can compare those two tables from the literature, and then we're also asking you to calculate the modulus of resilience and the modulus of toughness for the specimen as well, all of which you can do based on the measurements that we give you pre and post testing, and also based on the Excel sheet that has the load displacement data. Okay, so good luck analyzing the experiment.